Hello guys, welcome to the continuation of our previous lesson on homogeneous differential equation. Today we are looking at solutions to homogeneous differential equation. Please, if you've not watched the previous lesson, I advise you to go and watch it before watching this tutorial. That will give you a general idea on what homogeneous differential equation is all about. We're going to solve few examples on homogeneous differential equations. Let's start. Our problem here says solve the differential equation y prime equals x squared plus y squared all on x squared. First of all, you can see clearly that this is homogeneous differential equation, because when you test it, put lambda squared here will be lambda squared. When you factor, get lambda squared also come out, and the degree will be what? 0. So it is homogeneous differential equation. Solution. We can change this to dy dx, because for you to solve a homogeneous differential equation, we need to change or transform this to separable differential equation in terms of variable u and x. So in that case, we are going to let the y equals ux. Then if that is the case, then our dy dx is going to be x squared plus ux all squared on x squared. And you can see that when we simplify, we are getting x squared, and here will be 1 plus u squared all on x squared, of which this will go. So now we have dy dx equals 1 plus u squared. Let's label this as our first equation. The next thing is to convert this, that's from y equals ux. We are changing this one, we are trying to find the derivative of this. So first we need to differentiate the y with respect to x, and that will give us dy dx. Now here we try to use the implicit differentiation. So we are going to differentiate the x with respect to x, and that will give us the u, plus differentiate the u with respect to x, and that will give x du dx. Let's label that too as our second equation. Now let's equate the two equations. This is because equation 1 is dy dx and equation 2 is dy dx, so we can equate them. Equating them, you are getting 1 plus u squared equals u plus x du dx. So let's move this to this side. The u's, we are getting 1 minus u plus u squared equals x du dx. At this point, we can separate the variables. So separating the variables, when we take this one to this side and divide by the x, we are going to get the x on x equals, then this side to this comes, we are going to get the u squared minus u plus 1. Let's rewrite it in another way. So now that we have been able to separate the variables, we are going to integrate both sides, and you know clearly that when you integrate this, we're going to get ln x, but we have to work with this one out. So considering the left hand side, you realize that the integral of 1 on u squared minus u plus 1 is better solved using the trigonometric substitution, because the denominator u squared minus u plus 1 is an irreducible quadratic expression. In other words, this particular function cannot be factorized that easily. So using the method of computing the squares works better. That will lead us to trig substitution. Using the method of computing squares, taking the denominator, we have u squared minus u plus 1. And you know from that we need to find half of the coefficients of this. And that we are adding the half of that squared, then subtracting the same half of that squared. Which, you know, when you consider these three terms, it will lead us to have u minus half squared. Then simplifying the whole of this, we are getting 3 on 4. So let's take this to replace what we have here. Note, from trig substitution, you learn that when a constant a is being squared minus a variable u also squared, we let the variable equals the constant sine theta. Then you have a constant squared plus a variable u squared. Also, the variable equals a tan theta. And you can see this. You can see that this looks like what we have here. Though over here we have minus another constant, but it looks alike. This squared plus that. So we need to just rewrite this one to be in the form of this. Though we have other forms, but we consider only these three. These are the commonly used forms. It means we are going to get integral of the u on u minus half squared plus. So let's convert this one to the squared form. And you simply know that we are going to apply square roots. 3 on 4 all squared. So now we can say that let u, the variable part, all of that equals the constant root 3 on 2 tan theta. Now we need to find the derivative of this. So when we try to differentiate this with respect to theta, we are going to get the u d theta, and then we differentiate this, go to 0, equals, now when we differentiate tan theta, we are going to get 3 on 2 sec square theta, which our du will be equal to root 3 on 2 sec square theta d theta. We have the du. We can back substitute. Integral, we had here our du is now this, and then our u minus 1 on 2 is also this. Bringing this into the expression, we are getting now this is that, as I said. So we're getting root 3 on 2 tan theta squared plus root 3 on 2. Simplifying the denominator, we are getting integral of root 3 on 2 sec square theta d theta on root 3 on 2 all squared tan square theta plus root 3 on 2 all squared to also give us 3 on 2 sec square theta d theta on, so this will give us 3 on 4 tan square theta plus 3 on 4. Let's try to bring this constant to the back of the integral sign, and then factorize this and this also out and bring it back to an integral sign, and that will give us root 3 on 2. When we bring it, we are going to get times 4 on 3 because it's dividing. So if I want to introduce multiplication sign, I will reciprocate it. Integral of sec square theta d theta on tan square theta plus 1. Simplifying this, we are getting 2 root 3 on 3 integral of sec square theta d theta on. Then we know that this from trig identity is the same as sec square theta. So we can cancel out sec square theta, and we are going to get 2 root 3 on 3 integral of what? The theta. So with this, let's integrate. Integrating, you are going to get 2 root 3 on 3 theta plus c. So now our function now becomes, the integral of this is what? Ln x plus ln c equals, and then now the whole of this, we had 2 root 3 on 3 theta, but our u minus half equals root 3 on 2 tan theta, of which tan theta is going to be 2u minus 1 on root 3. When we rationalize this, we are getting tan theta equals 2 root 3 u minus root 3 on 3. Find the theta. Theta becomes tan inverse of the whole of this, and that is, so now that we know the theta, we shouldn't also forget that, again, from y equals ux, we can find the u, because everything was supposed to be in terms of x and y, but our original question was in the form of x and y. So let's try to substitute this u. We know that our u is going to be y on x, so substituting, our theta is going to be arctan of root 3 y on x minus root 3 all on 3. Then let's simplify that. Theta is going to be arctan of 2 root 3 y minus root 3 x all on 3x. So with that, we can confidently say that when we simplify this, I'm going to get ln cx equals our 2 root 3 this on 3 arc tan 2 root 3 y minus root 3x all on 3x. And we can even go further to say that our cx is equal to e power 2 root 3 on 3 arc tan of the whole of this 2 root 3y minus root 3x on 3x. And that is our solution. It seems very complicated though, but with constant practice, you'll be able to adapt.